How you feeling? It's Thursday? Is today Friday for anyone? It's Friday? Yeah? Nice. Okay. What's that? The ASTR, right?
I look like a nice one.
Oh.
From last week.
Last week?
Yes, this is from like weeks ago.
Had just in case I started studying, I just wanted to follow it.
Oh, nice.
And I'll
You remember this class?
well, the two classes had this midterm at the same time.
How's that possible? Same day or same
No,
time?
they're consecutive days.
Oh, okay, yeah.
What came before Pluto? Stuff you're supposed to know to call Pluto.
What do you mean?
Well, after the midterm,
Mm-hmm.
we started talking about something, and then we talk about Pluto. What do we talk about?
Jovian plants. Jovian
Oh,
plants?
yeah.
So if you look in the content schedule, it's organized by week too. So it should have all the stuff there. If you see any issues with it, let me know, okay?
So I can start doing everything, you thought?
Yeah.
No, I mean, on 3 classes, I did all the tests for everything. So I concentrate, that's what I go on.
Yeah, good, nice. Okay, so I heard that this looks like an eye. Is that correct? Yeah, definitely. What do you think is supposed to be right here? Blocking out. Star, 1 star, maybe? So like, if you ever look at the sun, don't do it, that's how you burn your eyes. You like cover the sun, and then you can like see stuff next to it. So that's essentially what we're doing, but we do it very sophisticated. We use what's called the coronagraph. It like makes it so you can't see the star in the middle. There's something else in this picture. Which one? This one?
Yeah.
Yeah, that's where my eye went to, but that's not it. There's a planet in this picture.
Is it right there in the center, like that, the one?
This one?
No,
This one?
perfect.
This one?
No, to
This?
no, to the right. Right, the one, the little dot right there.
Where?
No, go up, to the left, That down, that little dot right there.
No.
Oh.
Yeah. This one? This one? No.
Is it way low?
No. It's real hard to find. The whole exercise here is that it's really hard to find. There's a couple things that I want to point out in this picture. One, you said it looks like an eye, right? So there's like a spear here. And then what else makes it look like an eye? What about the shape? Yeah, it's like an oval. So it's like a pupil, right?
And the iris too.
Yeah.
Iris too.
So this would be like the eyeball, and then this is like the pupil in the middle, and then this is like the eyelid.
Where's the iris?
What?
Where's the iris?
And this is not an eye.
But where would the iris be?
These ones here. That would be your eye if it was a space eye, but it's not a space eye. Okay, so this is dust. Okay. Giant amount of dust. And that's why it looks all like liney like that. All lines coming off of it.
Well,
So-
how do you make that form?
What? What you mean, these lines or the circular one? Like that?
Yeah, it's dust.
So what's happening is it's being illuminated by a star in there. And all of the sunlight is coming, not sunlight, starlight is coming out radially. Okay, and so it's finding the dust and then it's being bounced back into our eyes. Okay,
What's funny?
light's moving along these lines,
Oh,
and this is our planet.
oh,
That was super easy to find, right?
where goes to?
So in fact, this is really hard to find, so it's only really findable when you look at different observations over different times.
I have one more question. How do you know that it's one? How do you know that could not be more than one? I mean, you find one, how do you know that it could be anywhere else?
Yeah, I'm gonna talk about that. Okay, so when we look here, we see the same way that we looked at asteroids or Kuiper belt objects. And we were looking at the sky. We were looking for differences between observations maybe taken months apart or years apart. And we would see all of the stars would stay there, and then something would move across them. And similarly, we take a picture of this part of the sky 2 years apart, and we see that that little dot right there has moved in this direction. You keep watching and you keep watching, and you can watch it move all the way to the right. Okay, so we can see planets around other solar systems. We're going to talk about that next week in a lot of detail, but it'll allow us to test our theories of planetary formation.
I have one more question. What happens if somebody bombards in the Neptune?
What?
What happens if somebody bombards in the Neptune or something hits that?
We'll talk more about Fomalhaut B. It's not having a good life. I'll tell you that much. So we've talked about how like Saturn's rings. What were Saturn's rings created by? What's that? Gas and dust. Yeah. But like Uranus's rings are also created by gas and dust from the moons. What makes Saturn's rings so unique? They're very bright and really beautiful. They probably were recently destroyed moon. Geologically speaking, there was probably a really nice, beautiful, icy moon. It moved too close, got torn apart. And that makes Saturn's rings. Because we know that the individual particles there, they decay with time. They leave the system. So here we see a big old ring around this object. And that tells us that maybe there's a planet that's having a really bad time. Okay,
Would it be that
Oh,
little
that's what
small
the
one?
ring
say that again.
Or would it be that little?
It might be that little small one. Yeah, it might be going through a really hard time in its life and actually might be disappearing. So as it moves along this path, material from it is being taken off. I'll show you another picture of it on Tuesday.
Yellow and.
Yellow and red. Oh, that's an artistic choice.
Oh.
This is like this is a telescope image. So this is telling you that it's bright. Yeah, this isn't like actually telling you the true color. Sorry.
So, if it has a ring, then it's most likely going to be a planet.
Yeah, so some rings, like we saw on Tuesday, they show you the places where there are gaps in the rings are places where planets are currently being formed. In this particular circumstance, this is probably planets that were formed and now they're being torn apart.
Wow.
Okay. Cool. Not cool. Okay, we'll talk about more planets. So let's talk about the solar nebula. This nebular theory had 3 parts to it. It said that we started as a giant gas cloud, and then we started to shrink. As we shrunk, 3 things happened. Spun around, got fast. We got hot by compressing all of that gas. And then we made ourselves into a disk. I say we, collectively, not actually us. We weren't there. And so this is an example. Here you see another disk, an example of a disk. This probably comes from the fact that most of this material is already in the disk, and then it starts to interact with one another and doesn't get pushed up. Okay. Most things that we see in our solar system tend to be disk-like. So you look at Saturn's rings; those are very disk-like. You look at the plane in which all of our planets are in; that's very disk-like. You look at the moons of Jupiter; those are in a disk, right? And only the weird stuff is not in a disk. we talked about where comets come from, like the Oort cloud comets, the big sphere. So that doesn't make any sense yet. Okay, we'll talk about why that might make sense later. Okay. Okay. So there's another part to this. We talked about the orderly motions. I'm going to assume that based on the lack of questions, that people get orderly motions. Yeah.
Let's go back.
Okay, let's go back and let's talk about it. What questions do we have about orderly motions? Yeah.
I guess just when you mean collapse, like, and also related to like heat, I guess.
Yeah, so we think about it in the context of like, what does it mean to be hot? So when we define something like hot, it just means that the individual atoms, they're moving around really quickly. And so if you take any gas cloud, let's say a hot air balloon here, okay? And you confine how much space it can have. And then you add heat to the bottom, right? All of the individual ones start moving around more and it becomes denser and it rises, everything's good, right?
Expand.
The opposite of this is true here. So as this is very large, very undense, as it starts to contract, now all of those collisions between individual atoms happen faster and they have more energy. So it's just like if you started at the top of a hill, okay? You move down to the bottom of the hill, you're gonna have more speed. The whole gas cloud is doing that same thing. All of these particles are moving towards the bottom of the hill, and they're all moving faster, and so we think of it as hotter. Now, if you were standing inside of the solar nebula, you would not be like, oh, it's so nice, right? Still be freezing, because the densities are really low. There's no water, no atmosphere, right? But it's like hot. Okay. And then at the very center, where there's the largest concentration of mass, that's where you get the star.
What?
The star. Okay. Any questions about this? Does this one make sense? That might definitely be. Why is it a disk? Yeah, I hear kind of both what I want to hear. Can you explain a little bit more? What's the right analogy? Is it pizza?
No.
No. Is it just gravity alone? No.
No.
Okay. What's the third option? What was the analogy I used?
What did you do?
Yeah. Yeah. So if we're all walking around this room together, everyone's walking around this room, and then most people are walking this way, and I keep hitting the people, right? I'm just going to eventually change my mind and walk in another direction. If there's a preferred direction, collisions begin to force a preferred direction. And you can imagine, like, there might have been like some group of particles going this way and a different group of particles going this way. And maybe those two were doing really well, but eventually they're going to hit each other and they're going to choose one. Right? It's very rare.
So does it come like that they change direction? Like, from one end at the end?
Yeah, so you start with totally random motion. And as the thing gets smaller, more and more collisions, right? You have more and more particles end up going in the same direction.
Spinning around.
Yeah.
Like how fast, do you know how fast those things are going?
Yes. But they won't be meaningful to us because the scales that we're talking about here, right? This is already a built system. That's like several AU, 40 or 50 AU, I think. The scales for solar nebulas are like light years. So the amount of gas that originally makes us, an enormous amount of gas. We have to concentrate it down. Yes. Okay. Next. Two kinds of planets. What are the two kinds of planets?
Yeah.
Terrestrial.
Terrestrial Jogan, and that means
Oh, yeah.
rocky and gassy. I want to be like really simple here, because that way, like if I need to explain it to my kid cousin or something. Thanksgiving's coming up, we want to have something fun to say at the table. Okay. So why are there two kinds of planets? That's what we want to understand here. So let's look at some things. Oh wow, that's funny. I didn't do that. Okay. What are they made of? What are they made of? So on the left-hand side, hydrogen and helium gas. Don't actually make your balloons out of hydrogen. What happens if you make your balloons out of hydrogen?
Yeah,
Famous
they blow
example.
up. They blow up.
They blow up. Famous example.
Hindenburg.
Up.
Hindenburg.
Hindenburg. Hindenburg was a disaster where they filled it up with hydrogen, caught fire, killed thousands of people.
They should
Okay.
make you.
And then here we have hydrogen compounds. So those are the things that we like personally. I like water, H2O. And then you have some stuff that is not, I mean, ammonia is good for cleaning with, so that's hydrated nitrogen. And then here's carbon with hydrogens on it, that's methane. And these hydrogen compounds, where do you normally find those in the solar system?
Do the whole thing.
The whole thing, equally?
Yeah, they should be.
Ammonia, mostly gaseous planets.
Okay, so you found some in the gaseous tops of the planets, right? What about surfaces? Did you find any ammonia surfaces in the inner solar system? I think so. No. Okay, what about rocks? Where do you find rocks? Pressure planets, definitely, because they're called rocky, good. Okay, what about metal? Rocky planets, okay, I'll take that, we have metal planet. Okay, so these are the 4 different types of stuff that we can build from. Everything else just falls into those categories.
What are actually the rocks? And, the other ones, what are those made of? Is that what they are made of?
Rocks.
Right?
Rocks are made of rocks. We can get into what every single type of rock is, but I'm not a geologist, but it's hard stuff. My definition of a rock is, can you stand on it? Now, that's not a very good definition, but it's pretty close. Okay, hold on, let's go back one more. So typical condensation, what is condensation again?
Vapor.
Yeah. So we're thinking about what process? Solidifying from
Oh, solid to liquid, or liquid to solid?
liquid to solid, yeah. Condensing. Right? Can be even from vapor to solid or vapor to liquid, right? It's a phase transition going from something that's vapor to something that's no longer vapor. Okay. So a lot of people talk about like the condensation on your drink. It's really cold. Okay, a really cold drink, water vapor in the air goes, I want to hang out, and then it becomes liquid on the side. That's condensation. Okay. The opposite is true. So it gets really hot. We call that, like if you have water, it gets really hot and then it becomes water vapor.
Sublimation? No, that's.
Evaporation, right? So it's evaporated. It's like when you sweat, you get cool. It's evaporative cooling. So these two processes go back and forth. And so when we say condensation temperature, I want you to think about them as happening in both directions. So if it gets too hot, the object that was ice now becomes vapor. Or if it gets too cold, the object that was a vapor either becomes a liquid or an ice. That makes sense? Okay. So here, hydrogen and helium do not condense. They're only ever gas. Here, hydrogen compounds, they condense pretty rapidly. So anything less than 150. Okay. Rocks condense between 500 and 1300 degrees. So on a day-to-day basis, you're really not finding 1300 degree temperatures. So you find most of your rocks in their condensed forms. If you're finding rocks in a vaporized forms, let me know. That's bad. Right? That's temperatures above 500 degrees. Metals down here, 1000 degrees, 1600 degrees Kelvin. So these are super high temperatures where metal decides, I don't want to be metal anymore, I'm gonna be metal vapor. Kind of
So
mean,
it has to be pretty hot for that to happen.
yeah. And when we talk about certain giant planets, not here in our solar system, but in other solar systems, you can have metal rich atmospheres such that their temperature is like 2,000 degrees and it rains diamonds. Cool. Okay, let's ask a question. Okay, at 500 degrees Kelvin, what exists in solid form? Is it A, metals, B, rocks, C, metals and rocks, D, hydrogen compounds, or E, metals, rocks, and hydrogen compounds? Vote on 3, 2, 1. Okay. You want to turn to your neighbor, ask them what they got? See if you can get the right answer on them.
No, it's 500 feet. Yeah.
Okay, let's try and revote now. Revote on 3, 2, 1. Okay. So. Okay. Sorry, it's just dark. So no one liked hydrogen compounds?
No.
No one liked anything that included hydrogen compounds, and then everyone else was in this sort of region. You want to defend her in this one?
I picked 3 because even though at 500 Kelvin, some rock means movements. I guess you consider this a big one, 500 to 1300 Kelvin. There is some rock that can still be solid.
Yeah.
And then metal, of course, starts normalization at 1000 Kelvin.
Yeah, so I looked at it that same way. So I would say like, okay, so rock is just beginning to vaporize. If it's getting up to 500, right? Imagine that we're on in daily life. All of this is melted off already. That's all vapor. And we're just starting to make the rock evaporate. And so I agree. If I heard the argument for rocks or metals only, like metals only, you say, well, I don't know, 1300 is when most rocks disappear. So this one here, metals and rocks.
What's the reason why not?
Well, rocks can be solid up to 1300. It's only 500. You might lose some rock, tiny bit of rock.
But the rock has to start.
Okay, let's try a different one.
Okay.
At 100 degrees Kelvin, what exists in solid form? Is it A, metals, B, hydrogen compounds, C, metals and rocks, D, metal, rocks and hydrogen compounds, or E, everything? You know when you're ready to vote? Yes. Let's vote on 3, 2, 1. Okay, all right. Anyone defend this one?
Oh, I say metal because it's got 150.
Yeah, so metals would definitely be solid, right? What exists in solid forms at 100K? So that's less than this. So I agree with metals, but it's might be more than metals. Might be.
It says it's 100.
Okay, so hydrogen compounds condense at 150 or less than 150. And so at 100, you would expect them to condense. I agree, yeah. And all of these have already condensed too. So it's sort of like in this direction versus this direction. Okay, so as we drop the temperature, we're not worried about rocks anymore. They're not melting. And we pass the point where hydrogen compounds would condense. We're not worried about them anymore. What about helium? Do you think that's gonna condense? No, it says it can't. Okay, so it can't. I promise you it can't.
What's the answer now?
So it's D. Metals, rocks, and hydrogen compounds. Okay. Okay.
Also, it counts everything they came before.
Yeah. So think about it this way. So this is decreasing temperature and this is increasing temperature. Okay. I'm gonna skip this and we might come back to it. How do we build the planets? Okay, so this is gonna take a little bit of maybe I should put a different slide. I want to create an analogy, right? You got heat coming from the sun. It's your only source of heat essentially. The disk itself is a little warm, but you're mostly getting heated from the sun. And so if I'm standing way far away, compared to if I'm standing really close, which one's warmer? Far away or close? Close. So it's like a campfire. Stand close to the campfire, I get really warm. I walk far away from it, I get cold. That analogy still work here? Even though we're in a gaseous disk?
Yeah.
Okay. And essentially, if I go back to this idea right here, this is like a specific location. Because as I continue to get closer to the sun, I get hotter and hotter. Versus if I move farther away from it, I get colder. So there is a line in the solar system at which the temperatures get too hot for hydrogen compounds to condense. Can I say that again? Okay, so if I walk backwards here, let's keep in mind 150. Okay, 150 is where hydrogen compounds can condense, like water. Goes from water vapor into water ice. Okay, so if I start out here, it's all good. It's really cold. Okay, and then as I walk towards the sun, it's getting hotter and hotter and hotter. And eventually, instead of being ice, I become vapor. So there's specific locations where materials will change from being a vapor to solid. Okay. So that's condensation, formation of a solid or liquid particle from gas.
That's actually how the planet develops.
What?
That's how the planet was developed.
Yeah, we're gonna talk about that. So here you have a much hotter temperature in the interior of the disk, and here it's much colder. Okay. So inside of the frost line, rocks and metals do condense. Right? So rocks and metals, how hot did it have to be for a rock to condense? 500. Yeah. So that really doesn't happen until you get close to the surface of the sun itself. So rocks, they have no problem. They're living their best life. The hydrogen compounds are like, nope, I'm out. Okay. And then out here, you still have rocks. Life's still good. But now you also get hydrogen compounds. Okay. So that seems simple, maybe difficult. And we're going to play with this idea when we build the planets. Okay, we're going to look at the four main ingredients by mass, relative abundance.
It's rocks everywhere.
It's not rocks everywhere.
Okay.
So the first thing that we're going to look at, is the relative abundance by mass. when we talked about the astronomers periodic table, we said that the most abundant gases in the universe were hydrogen and helium by large fractions, right? And we see hydrogen and helium make up most of the mass in the solar system. Not surprising.
The same for the universe, right?
Yes. Hydrogen compounds here make up only about 2%. 1.5%, 2%. Rocks make up only 0.4%. All of the gold in all of the solar system is just a tiny fraction of a tiny fraction of a tiny fraction. And metal is down here, so I guess that's actually iron. Okay, this is where the gold would be. Okay, so these concepts of how the mass is distributed and how the temperatures are is something we're going to dig in with the first lecture tutorial. Okay.
So but the rocks are scattered in different places all the way around.
Yeah, so there are rocks all the way through,
Yeah, there's all of them.
but here we look at the amount that we have available to us. Hydrogen gas, imagine that we start with it everywhere. There's a lot more of it, but it's not going to condense. Okay, as opposed to hydrogen compounds, oops, let's move back, which condense out here and make a much larger fraction of the available mass than rocks do. So if we add these two numbers together, I don't want to do that, 0.2 and 0.4, 0.6, okay. And then 1.4, that's about twice as much hydrogen compounds as there are rocks and metals. So as long as you can get from this place to this place, you have twice as much building material. And I'll show you that we're going to build from it in a few seconds. Okay. Okay, so let's do this one. Wait, what did I do? I'm going to take two for you and then we'll pass some around back.
So the rocks on the outside are going to start collapse.
This.
This.
Oh, okay. I'm gonna take like one. Okay. And if there's extras, I think people will want them. Did anyone need the Kepler's third law one? One asked me about it. I'm gonna have to get that. Okay, cool.
I'm noticing some classes start out hard and they get
What do you mean by that?
classes start out hard and they start getting easier.
When you understand the material better. Yeah. At least as far as we know. There's no like road ones that we're aware of.
The negative. Where they move. Negative 100.
That's fair. Yeah. Kelvin is fair. You wanna go for the Kelvin? Yeah, so there's like a fair and then a self. So remember that.
Like, very good.
So when you said like negative, negative.
Well, you have a table, you don't need to go now.
We're doing projection.
What's that?
Projection. Projection.
You're doing projections?
Projection.
Oh,
Something projected.
okay.
I did it right, so. On the one on the other.
Cool.
But then you can make movements.
Nice.
Start.
Yeah.
You want to So this, So did they say the range? Like a little minute, they had
It makes range regardless of whether or not there's a plan. Yeah. So a lot of the 33 systems that we'll look at, they can have multiple planets, some have many, some have zero. But they all form this kind of star.
So that is exactly what happens.
We'll talk about that, yeah. What's that made of? Or what's the largest? What was the most made? What kind of gas? Hydrogen and? Very good. How about? I can do that.
The same way we try to compete, how much are your numbers in? When you import the point, how much are you doing?
What's that? Yeah, people have done this. Yeah, those are Einstein equations. We'll talk about that if you want to talk about that. Okay, how are folks doing? Almost there? Your question? Yeah. That's. Yeah, sometimes they do the night edition. Yeah. Okay, folks. Should we put some of this to use? Center our brain? All right, we're gonna do it anyway. Okay. Sorry, I'll read it. Okay, astronomers have discovered a massive giant planet, like Jupiter, orbiting stars at closer than 0.7 AU. So that's about where Venus is today. Why don't astronomers believe that these gas giant planets originally formed at those locations? Is it because A, the planet's gravity would have been too large to form that close to the star? B, the temperature in the early solar nebula was too high at those distances? C, the orbital periods are too long for them to be located that close to their companion stars? Or D, the young star's solar wind would have blown the planets farther away? Let me know if you're pissed and you're ready to vote. Might be related to what we just did. Might. All right, let's vote on 3, 2, 1. Okay, of the people who answered, you all answered the same. Impressive. Okay. So the temperature in the early solar nebula is probably too high at those distances, right? So Venus, for example, can't incorporate hydrogen compounds. And so we don't think Venus could ever have gotten as big as the gas giant planets. Let's talk about what we do think happened. Okay. So you start with a whole bunch of stuff. And all that stuff likes to clump together. So you think about it in the context of like that analogy I had with all of us walking around in the room, but now we're all sticky. And as we bump into one another, we become one piece. And those pieces that are bigger will bump into more small pieces and absorb them.
And they all go the same direction.
Yeah, and they're all gonna end up going in the same direction. So here you start with a bunch of little small ones, and they get clumpier and bigger, and then you end up with all of these individual planets. That's not to scale, of course. This process is called accretion. So when you add stuff to you, small objects together become bigger. And you start with something called planetesimal. All that word means is like a little bit, little baby. So going from little baby planets to big planets. Okay. So then what happens when you get really big planetesimals? Okay, so stuff that is much larger than the mass of the Earth. And you might be thinking to yourself, well, planetesimal, we're a planet at like 1 Earth mass. So this is really talking about how like massive planets are forming. 10 to 20 times the mass of the Earth. Let's recall, for example, that Jupiter is like 200 times the mass of the Earth. So that's a pretty big jump. You go from 10 times the mass of the Earth to 200, you have to do something special. Well, eventually what happens is you are living your life, you're moving around the sun, 10 Earth masses, you start to grab the gas and dust. So the dust you were already picking up, you're flying into it, but the gas is now going to start becoming, so instead of, when we look before this part here, so we said, the hydrogen does not condense in the nebula. So terrestrial planets have no way really of incorporating it into their bodies. But if you get massive enough, you can start to grab it directly from the solar nebula. And you can use it to start getting bigger and bigger and bigger. So just like stars form, when enough material falls onto them, they start pulling more material towards them. Gas giants are going to start doing something very similar. Now, usually gas giants don't end up then undergoing like fusion, making stars. But you do see some circumstances where you have multiple stars forming next to one another, something called the binary, or even a triplet system, 3 stars all going around one another. And this is happening because they're pulling in all of this mass, all of this gas.
What's Pleiades?
These are separate stars.
8 of them.
There's 7 separate
What's
stars.
that?
Separate. Okay. Did that process make sense? Okay. So stuff that is outside of the frost line, that temperature difference that I told you about, 150 degrees, has extra material to build with. And so you might be thinking to yourself, well, Earth is kind of big. Why didn't Earth become a gas giant? And that's simply because it doesn't have enough material to get above this limit of 10 to 20 Earth masses to start to grab gas from the disk. You have to already be massive in order to get more stuff. Right? It's like the rich get richer, but it's planetary formation, rich get richer. Okay. Okay. And so when we look at them like this, okay, there's Earth. There's these little cores that we think exist in the gas giants. And we think about them in this context as like having a little rocky core in the middle. We think Saturn definitely has it. We don't know if Jupiter does. I think Jupiter's might be totally melted, just like gone, because the pressures are so high there. But if you look at Uranus and Neptune, they do have these small, essentially rocky cores. Now it's enormous amount of pressure, so it's not rock in the way that we think about it. But they have these giant envelopes outside of them that are primarily made of hydrogen and helium. And then at the top, you might have your like ammonia, methane, depending on what color you're looking at. Okay, so if I stopped you on the street and I said, hey, why are there 2 different types of planets? What would the primary argument you make there? Not enough material where?
For example, like Earth doesn't have enough material to be bigger.
Yeah, so Earth didn't have enough material to be bigger because it wasn't big enough. It could never grab gas from the disk. So it sort of limited itself. Okay. Okay. And so this was this question, I think from like a couple weeks ago, a couple classes ago, maybe a couple weeks ago, is like, why are all of the planets, why are all the moons around Jupiter in a flat line? And that's because here is this little proto-Jupiter, something that's about to be Jupiter. It makes its own little disk because it's spinning, and the gas is moving from far away to it towards it. It speeds up, and it creates common motions around it, and it starts to form a little disk around the sun. There's a disk that it lives in, and the disk around it. And in that little disk, you will see the planetesimals going to collide together. They're going to form Io, Europa, Ganymede, and Callisto. It's disks all the way down. Process makes sense? Okay. So why are there only 2 types of planets? Well, it has something to do with the fact that we have a limited amount of stuff to work with. And importantly, temperature is dropping as we move away from the sun. We move away from the sun, temperature goes down, and I can start to build more things. There's only a small amount of rocks and metal, and that makes sense. There's small terrestrial planets to be built from. There's lots of rocks, metal, and ice. Once I add ice in there, then I can start to grab hydrogen and helium, and there's tons of hydrogen and helium, so I can get as big as I want to get. Okay. We did it. Any questions before going to the next one? Okay. So there's two types of small bodies. Hold on. Go back one. What are the two types of small bodies? Comets and asteroids primarily, yeah. Okay. Okay. It's a long one, I bet. So remember the amount of building material present in the early solar system. We had 0.6 rocks and metal, 1.4 ices, and 98% gas. So how would things look if there had been a lot of rocks and metal, but only a small amount of hydrogen compounds and the same amount of gas? But what I'm doing here is I'm taking most of the mass in the hydrogen compounds and I'm turning them into rocks and metal. So the options are A, large rocky planets close to the sun, few small icy planets in the outer solar system. B, gas giant planets with rock metal pores close, gas giant planets with rock metal icy pores far. Sorry. C, gas giant planets close, large terrestrial planets far. Planet composition is the same. D, large terrestrial planets close, small gas planets far. Or E, no different than it is now, and this is a lot of reading for nothing. This one will definitely get the test. Without a doubt. It's just too, I have to, right? I'm not even gonna pull you. Why don't you start by asking your neighbor to see if you guys got the same answer? If you're thinking about it the same way, and then we'll pull one. Do I have one already? Do you have a question? I can clarify anything. Okay, how do we feel? Ready to vote? Maybe. Okay, let's show me your hands if you're ready to vote. No, not ready to vote. Okay, let's try it anyway. Vote on 3, 2, 1. I'm gonna walk through this one. Okay. There's every single person answered differently. So there was no like grouping around one thing, and I'm not gonna have you attempt to argue it. So if I were to answer this question, here's how I would approach it. Okay, so rocks are the ones that are condensing closest, but they're sort of still everywhere, right? Okay. And ices really help you get over that problem of not having enough material to begin to suck in gas and hydrogen and helium from the disk, right? So you only get those gas giants once you get past the frost line, where you can condense that material. So you can get large enough, you can get enough gas. That was the argument. Okay. Now I switch it. And I say, well, I don't care about hydrogen compounds at all. Just lots and lots of rocks. Many rock, many metal. Okay. So large rocky planets close to the sun. Kind of sounds good. Right? Because that means rocks, lots of rocks. I like that. Few small icy planets in the outer solar system. Okay. I don't really know about that one. Let me come back to that thought. Gas giant planets with rock metal cores close. Gas giant planets with rock metal icy cores far. How would that happen? Well, I could look at that and I could say, if I had rock metal cores, if there were massive rock metal cores, maybe right away I start to grab gas. And so maybe I get gas giants all the way out. Okay, I'll think about that one a little bit more. Gas giants close, large terrestrial planets far. That one doesn't quite make sense to me. That's sort of opposite. So I can get rid of that one. That one's bad. Large terrestrial planets close, small gas planets far. One also doesn't quite make sense to me because gas planets are always at least larger than the terrestrial planets. So get rid of that one. E, I don't like that one because I made a difference and I told you it'd be an exam problem. So I'm gonna get rid of that one. So now I'm down to these two. Okay, so I got few small icy planets in the outer solar system. So that doesn't take into account at all the fact that they are still rock in the outer solar system. So it's true that there isn't a lot of ice, definitely, but there's plenty of rocks. So I don't like this one as much anymore. So this is going to leave me with D. And the core's interior there is going to be what matters. Rock and metal close, and a little bit of ice in the core far. Just a little bit of ice. And you'll never see it, so maybe it won't matter. But it's going to change the density slightly as you move out into the solar system. Make sense? Okay. So now the question is, do you feel like you could make that argument back on a test? Like, what if I changed one of these? Oh, don't be mad at me, I have to ask. Okay, so what happens if like I get rid of all of the rocks and metal and I turn it into all hydrogen compounds?
All gas.
All gas planets where? Close, far? Far. Do we have any close planets? No. Oh, so you could do it. You got mad at me. What's that? Yeah. So, okay, so let's talk about that in a few seconds because we haven't even talked about the gas, right? Gave you this material, said run with it. Okay. So the solar nebula is forming planets and there's still stuff laying around. And we haven't even talked about why there isn't stuff laying around. Right? Your point exactly. Is there gas all the way up to the surface of the sun? I haven't said that. Right? So there's gas in the original nebula, which is forming the gas giant planets. And there's junk. The leftover, we talked about the sawdust for making your own table. Okay, just leave it all over the workbench. So now you have to do something with it, right? Okay, so what happens to the gas? And this is a real picture, okay? 0.5 light years, massive star. And there's a little star here that's forming. And it has a disk, or it had a disk. And this nearby star is basically bullying it, and it's blowing away the disk. So just like blowing out a candle, this star is putting out solar wind, strong solar wind. We talked about the fact that that's like little particles They're coming off the surface, electrons, protons, helium atoms. They're moving really fast and they're pushing material. So the gas that used to be around us was living its best life, orbiting with us. And then the sun was like, and blew on it for a long time, and it said, bye. It blows away gas. Solid material, it doesn't really care so much. Especially big solid material. So if you're like an asteroid, you're not feeling the effects of solar wind. You don't care. It's just like little pieces of dust and gas. Tiny, tiny pieces of that. Okay, so your original question about, well, where's the gas? The gas originally is right up to the star. This whole thing is all gas, all the way down. Okay. Questions about this? Okay, so what happens to the junk, the sawdust? Well, we already saw that a little bit. Asteroids. Asteroids are the rocky sawdust, the rocky stuff that's left over. This stuff here wanted to become a planet. That's what the asteroid belt wanted to do, and it just kept getting into basically a spat with a fight with Jupiter. Every time that it would see Jupiter at the Venus store, they'd get into a fight, and Jupiter is much bigger, and so this planet was constantly getting beat up, and then just was destroyed. So we don't have anything past Mars. Okay. All right, and then we have one more. We have comets. So if you're cold, you can have comets that come from two different places. Here's the Kuiper belt, and here's the Oort cloud. We talked about that when we talked about comets. And these ones in here, they go around us in the belt, just like the asteroids do. They're just made of the hydrogen compounds. So they are mostly going around circular orbits. They're going relatively slowly. When they collide with one another, we saw that really, really funny joke that I made about the potato. Right, you saw, remember the thing about the potato? This is a different potato joke than the potato and the pea joke. This is the one that we looked at Arrokoth, which is a Kuiper belt object. And we looked at the surface, there wasn't these violent impact areas. They look soft. They look like, gentle. Because everything's moving really, really slow out there. As opposed to asteroids, much, much closer to the sun, they're already moving really quickly. So when they smash into each other, you get lots of small fragments. And then you have these randos. They're way out here in the Oort cloud. They're moving really, really slowly, going in all directions. When I say random, they literally mean. Some of them are going backwards. Some of them are coming up from below. They're great. Right? So what are they doing out there? We're going to talk about that in a few seconds. Maybe. Okay. Did I say it? Oh yeah. This is maybe alluding to that. Can I just do this? Yes.
What was yours about?
I had this. What did I do? Okay. All right. Yes. So what would have happened? So let's go back here for 1 second. Okay, so this solar wind blows away the gas and dust. It still doesn't happen right away. It obviously has to exist for long enough for us to get Jupiter-like planets, right? So there's a time scale. And I'll tell you that it's on the order of millions of years. You have a couple million years to build your planets. Okay? And after that, you won't have any gas to build from. So what happens if the time scale is shorter? Okay? So let's say you start forming, condensing, and accreting material. But then the solar wind turns on much faster than it does in our solar system. What change would that have? Would A, all the planets have much thicker atmospheres? B, the Jovian planets not be as large? C, the terrestrial planets not be as large? E, Earth's moon would look different? Or, sorry, E, there would be more asteroids and comets. Ready? Let me know when you're ready to vote with your fist. Let's vote on 3, 2, 1. Okay, so we got 2 camps. 2 camps. Don't want to defend their decision. A camp of people from 5 and people from 2.
The solar wind would push the gas out, which means there wouldn't be as much gas, so that's why the plants would be smaller.
People agree with that? They're very confident. Yeah, that's good. That's correct. That's correct. That's absolutely correct. So the solar wind turns on, right? And you don't have as much material to build the plant. That makes sense? Cool. There might be more asterisks and comments, but that's not the point of this question. Now, if you wrote this on the exam, right? You wrote that as well. I'd be okay with it. You have to explain why you chose that. But I'm guessing that the people who chose it have very good explanations, right?
So the solar wind blows the gas off. Then. Oh yeah, terrestrial planets aren't big enough, so they won't see it.
Well, terrestrial planets don't have anything to do with gas. They don't even care. Earth's moon doesn't have anything to do with it. Earth's moon comes from an impact later. Planets will all have thicker atmospheres. When we talked about the atmospheric sources and sinks, say for the Earth's atmosphere, we said that that comes from impact cratering, so comets and icy asteroids hitting our surface after we're formed. So that has nothing to do with gas. So you're right that it only has these things. And really, it's this one that I cared about. Jovian planets being large.
So it wouldn't be,
What's that?
it wouldn't be.
It would be B.
Oh,
B is the right answer. Jovian planets would not be as large because they don't have as much material to draw from. Okay. We have exceptions to the rules. See if we can go through them pretty quickly. I don't know if it's a problem. We'll ask one more and then we'll just leave on a really high note, okay? What characteristic of Earth is not explained by the formation theory so far? Is it, sorry, the way that we've talked about it so far, nebular collapse being first, condensation, creating the little particles, accretion, the particles getting bigger, gas capture, not necessarily for Earth, but for the gas giants, and then solar wind clearing, moving that gas away. So which characteristic of Earth is not explained by this theory so far? Is it that A, Earth is composed of rocks and metals? B, Earth has oceans? C, Earth orbits the sun counterclockwise, same direction as the sun spins? D, Earth has very little hydrogen and helium gas? Or E, Earth is located in the inner solar system? Let me know if you're ready. This. Let's vote on 3, 2, 1. Okay. All right. How would I answer this? So these two actually seem very similar. Earth is composed of rocks and metal. Earth is located in the inner solar system. That's kind of saying the same thing. So actually, that's kind of explained by the condensation temperatures, right? Earth having very little hydrogen and helium gas is due to the fact that we don't do gas capture. So it's not those. Earth orbiting the sun counterclockwise, same direction as the sun spins. And that has to do with, where does that come from? What was that? Nebular collapse, yeah. So as we begin to collapse the nebula, everything starts spinning in the same direction, including the central star. Central star is spinning in the same direction with the disk. Okay, so that was actually explained, and so in fact, it is that B, Earth has oceans, has not yet been explained. Okay. All right, and we'll talk about why Earth has oceans next time. Any questions before you go? Okay. Okay, have a great week, y'all.
You just-